In this short video, I'll show you how to use the DWSIM software to calculate the products of a chemical reaction in the equilibrium stage. As we know, any chemical reaction proceeds theoretically in both directions. It proceeds in the reverse direction as well as in the forward direction. If the reaction is exothermic, then the reaction prefers to proceed in the forward direction. If it's endothermic, then the reaction prefers to proceed in the reverse direction. At some stage and after some time, we will reach the equilibrium stage in which the net rate of the reaction is zero. It basically means the reaction in the rate of the reaction in the forward direction equals the rate of the reaction in the reverse direction. If the reaction is exothermic, we will reach the equilibrium stage at a shorter time. If the reaction is endothermic, then we need a longer time to reach the equilibrium stage. So here we should distinguish between the kinetics and the thermodynamics effect on the chemical reaction. Kinetics is all about the time scale. In thermodynamics, we are just concerned about the final state. So when we write a kinetic models, it's mainly consists of the reaction rate parameters that are kinetics aspect rather than thermodynamics. But thermodynamics determines the entire likelihood if the reaction will proceed or not. If the reaction is highly endothermic, it will not proceed at all, for example. So both concepts are important to understand the extent of a chemical reaction. Here we are just concerned about the equilibrium mole fraction, which is a special case. Two methods to calculate the equilibrium concentration of a mixture. The first one is the stoichiometric method, in which we know the reactions. The second method is the non-stoichiometric method, in which we only know the name and the initial concentration for a species. The stoichiometric method is based on the equilibrium constant, that is a function of the Gibbs free energy of the reaction. Now the ratio of the mole fraction of the product divided by the product ratio of the reactants equals the value of K, basically. So we have four unknowns that are the mole fractions for C, D, A, and B. Thus, we need to convert these four unknowns into one unknown. This is called the reaction coordinate. So what is the reaction coordinate? It is a parameter that characterizes the extent or the degree that a reaction has taken place. For example, the initial mole, the mole fraction for any species in the reaction equals its initial number of moles plus its stoichiometric coefficient times the reaction coordinate divided by the total initial number of moles plus the total stoichiometric coefficient times the reaction coordinate. So we need to write the mole fraction basically in terms of the reaction coordinate. So all these equations are implemented in the DWSIM software. So let's apply the stoichiometric method based on this problem statement. We have a feedstock of N-butane that is decomposed at 2000 Kelvin and 1 bar. According to these reactions, N-butane gives us ethylene plus ethane. If the reaction reaches the equilibrium stage, what are the equilibrium mole fraction? Let's assume we have an initial molar flow rate at 10 mole per second. So let's open a DWSIM software, choose a new steady state simulation. Click next. We need to define our compound. The first one is N-butane. So click. Then we have ethylene. And finally, we have ethane. Okay, so click next. We need to choose the thermodynamic package. Let's go for Schwabe-Friedrich-Quanch. Click next. For the system of the unit, we need the pressure to be in bar and the temperature in Kelvin. So click create a new system of units. The temperature by default is in Kelvin, so let's leave it as is. The pressure in bar, let's call this new system of units as C14, for example. So click create. Finally, click finish. Now we need to define our equilibrium reaction. Go to setting, then to reaction, go to chemical reaction, click add equilibrium. We have chosen 3 species, so let's include all of them. The basis compound is N-butane because it's the reactant. The stoichiometric coefficient for N-butane is -1, for ethylene is 1, for ethane is 1. The basis of the reaction is basically a partial pressure. The phase is a vapor one. Then we need to click OK. Okay, we have defined our equilibrium reaction. Well, let's give it a name. Let's call it reaction 1. The unit should be in bar. I think everything is okay. The equilibrium constant is calculated based on the Gibbs free energy of the reaction. However, we should also be able to provide a constant value if we wish to. But for now, let's proceed with the K value calculated from the Gibbs free energy of the reaction. So click OK, close this one. Now drag a material stream. The temperature was 2000. Pressure is 1 bar. The initial molar flow rate is 10, for example. For the compound amounts, N-butane was 1, ethylene is 0, ethane R is 0, because in the statement of the question we have a pure N-butane stream. Click accept and change the name into feed. Now close this one and go to reactors, choose an equilibrium reactor. Click on the equilibrium reactor. For the inlet stream, it is the feed. For the outlet stream, click create and connect. For the second outlet stream, click create and connect. For the energy stream, click create and connect. And we can choose the calculation method. We wish to have an isothermal process. So from the calculation parameter, switch to isothermal and click on F5. The calculations are done. From the reactor, go to result, then go to reactions and go to the conversion. So conversion in butane, these conditions is completely converted. Now click on material stream 2 to check the products. So at 2000 Kelvin, and as expected, it is a very high temperature. 100% of N-butane decomposed to give us the product of the reaction, which is ethylene and ethane. Now we can also assume that we have an adiabatic process, and we would like to calculate the equilibrium mole fraction at adiabatic conditions. So click on the reactors again, change the calculation method into an adiabatic. Now click F5 again. Click on the material stream 4, for example. Let's check the compound amount. So at adiabatic condition, we still have a complete conversion of N-butane. However, from the feed, we can reduce the temperature. Let's see if the temperature is low, what would be the equilibrium mole fraction. Let's assume the temperature is 500 Kelvin. So at 500 Kelvin, the conversion of butane is very low, and the conversion of butane, if you click on the reactors, it's only about 3%. And these are the mole fraction of ethylene and ethane. So what we can do, we can plot the temperature against the mole fraction. So each time we change the initial temperatures of the feed, and we fix the temperature. We fix the calculation mode at an isothermal. So each time we fix the temperature, we have a different mole fractions. Thank you. This was the first part. Now let's switch to the second method, which is the non-stoichiometric method. In the non-stoichiometric method, we need to solve a set of equations that are based on the principles of Gibbs free energy minimization. Well, basically, this is based on the Lagrange method. In the Lagrange method, the software automatically solves a set of equations, and there are three types of the equation stored. The first one of them is the Lagrange method, and this Lagrange method it is based on the mole, the number of moles. So we need to write an equation similar to this for each one of those compounds. Then we need to write a mole balance for each one of the atoms, and finally the total number of atoms equal the number of atoms for each one of the species. So in principle, we need to solve a set of non-linear equation, and all this is implemented in the DWSIM software. So in this method, we only need to know the name and the initial concentration of the species. That's all. We don't need to know the chemical reaction. Let's solve for this example. Here we need to calculate the equilibrium composition at 1000 Kelvin and 1 bar for a gas phase system containing those species. We have 2 moles of methane, 3 moles of water, and at equilibrium stage we have 5 species. We have methane, we have water, we have carbon monoxide and carbon dioxide, as well as hydrogen. So once again, let's go to DWSIM software. Open and use steady state simulation. Click next. Let's choose all the compound. We have methane. We have water. Let's choose water. We have CO. We have carbon monoxide, carbon dioxide, and we have H2, hydrogen. Okay, click next. The thermodynamic package again is swap the SRK. Click add, then next. The system of the unit should be, for example, C14, and then click finish. So drag a material stream, open it. The temperature was 1000 Kelvin, I think. The pressure is 1 bar. The total molar flow rate was 5 moles because we have 2 moles of methane and 3 moles of water. In the compound amount, we have 2 moles of methane, so this is 2, for water is 3, for the rest are 0. Then click normalize to convert the number of moles into mole fraction. Then click accept. So we have defined our feed material stream. So close this one. Next, go to reactor and choose a Gibbs reactor. Gibbs reactors means that we are using the non-stoichiometric method to solve for this example. So note that we have not defined chemical reaction as we did in the first case. So click for the material, for the inlet stream, choose feed. For the outlet stream 1, click create and connect. Outlet stream 2, the same, click create and connect. The same for energy stream. So for the compound, we need to choose all of them. Click from the calculation parameters. Our case is isothermal, so choose isothermal process for the compound. Choose all of them. Then for the element, click create. Close this window. Now click solve. It should take a few seconds to complete. Now the calculations are done. Let's check the material stream and go to compound amount. So these are the mole fractions at the equilibrium stage. So we can see that the equilibrium stage prefers everything to be converted into carbon monoxide and hydrogen at these conditions. Now, sometimes we wish to see the effect of the temperature on these compositions. So we can change the temperature. Let's assume the temperature, let's increase the temperature. So if we increase the temperature, we would assume that the likelihood for the formation of the carbon dioxide should increase because it's the final combustion products. Let's change the temperature into 1500. And the calculations are done automatically. So let's wait for a few seconds. Now let's go for click on the reactors again, and the conversion should be higher. So click on material stream and let's check the compound amount. So the mole fraction for carbon dioxide increases slightly, and hence we can plot the temperature against the equilibrium mole fraction. Thank you. I hope that was useful. Thank you so much.